this computer. Excellent. So we share the screen. Okay. So last time, yeah, okay, we have the last person joining. So now we can start the lecture. So during last lecture, let me just look at my notes, what we could get. I think the last part, which was related to the detector, if I remember well. So the point that we simulated the action of inefficient detector with a beam splitter. So we say that there are many cases in which theoreticians, when they ask, when experimentalists, they ask them to simulate what's going on with an inefficient detectors. Usually what they do, they will change the coupling in such a way that the photoelectric will happen. So they don't place 100% of the time that you do detect photons, but this will be probabilistic, and among, let's say, 100 photons, only 80% of them, they will be detected, or only 20% of them will be detected. And that was eventually erased during last decades. So people, they fight to get a better detector in such a way that you can get any photons detected and not missing any of those. Why this is important? For many quantum optics experiments involving, for example, Bell inequalities and violating local hidden variables. And also in quantum technologies, when you deal with quantum communications, for example, you don't want to miss any of those information. Okay? How theoreticians, they simulate inefficient detector is just by using a beam splitter. This is what we learned during the last lecture. So essentially, let me remember that what was the definition of beam splitter that we had. We assume that we do have a beam splitter with a reflectivity of R and transmittivity of T, which those are the Fresnel coefficients. Essentially, then we had the action of the beam splitter, which was T IR, IR T, and then that was also the configuration that we had. It was A, B, how they will be linked to the C and D. Good, and then we say that it's better always to work with the inverse of this, because we want to link C, D to what's happening with A and B, and that was inverse of the action of beam splitter. And that is A and D, A and B. So eventually what we got from this was that C is T minus IR T A minus IRB, and also D is equal to minus IR A plus T B. And of course, the creation operator will be the same scenario. So it will be C dagger equal to T A dagger plus IR B dagger. And D dagger is equal to plus IR A dagger plus T B dagger. Okay, remember that A dagger, B dagger, they were creation and annihilation modes of port A and port B, and also any creation operators of the mode A, and B dagger and B, they were for mode B, and C dagger and C, they were for mode C, and etc. And we knew very well that A and B, they will commute with each other, including annihilation and creation operator. Consequently, C and D also, they will commute with each other. All right, good. And then we solved many different problems. I think we solved what's going on with a Mach-Zehnder interferometer. We built up the quantum action of Mach-Zehnder interferometer. We look at the wave plate as well, that what's going on with them. We feeded them with different photonic states. For example, we feed them with one photon, with n photons, with, let's say, we look at the Hong-Ou-Mandel, we look at the coherent state, and also as an exercise, I say to you, can you check what is happening with the thermal state? Okay. So for the action of inefficient detectors, we say that simply, if you have a detector, and I think we look at the situation that the detector work like. So when you have a photons coming in, then essentially, if the detector is perfectly working, I mean, having 100% efficiency, then you will produce an electric signal. And we talk about the version of the electric signal. It's some, depending on the detectors, can be few tenths of nanoseconds. That will be the pulse that you will create. And usually is TTL or NIM, depending on the electronic that you do have. I don't want to talk about those engineering. So what is happening that sometimes your detector does not click. And theoreticians, as we discussed, what they do, they simulate this with having a beam splitter at the front of your detector. What does this beam splitter do is just does not allow the photon to be transmitted always. So the probability of transmitting photons will be, let's say, eta, which is essentially given by t squared. I think we discussed about that as well. So the reflectivity, of course, will be 1 minus eta, which is r squared. Okay? Which we know, of course, that r squared plus t squared should be equal to 1 because we assume lossless beam splitter. We assume that the action is unitary. Good. So we say that what is happening if I want to detect m photons, m number of photons from n photon. So what do I mean? You are sending n photons. Let's go with n small. And then your detector only detects m of them. Good? That's a question that we do have, because your detector is inefficient. But we are posing the question that we look for explicit case when you have m photons. All right? So now let's look at the situation. We have a beam splitter at the front of it, and we know that if you have n number of photons coming in, then you have a beam splitter. Then we want to know what is the number of photons in mode C. So essentially, what we have n photons in mode A and 0 photons in mode B, right? And then we want to look at the action of beam splitter on this. So n photon in mode A means that you have creation operator, power of n divided by square root of n factorial acting on vacuum. Good. We have done all of these. I want to review because some people, they were not in previous lecture. We have done these in very details. So then essentially what we get from this is that now we have to link A dagger to the output ports. So then we have to look at the case when we have a dagger linked to the output ports. Then A dagger will be replaced by a T, essentially C dagger. Someone can correct me if I'm writing in the wrong way. IR D dagger power of n divided by n factorial. This was how we link the input to the output creation operator.
Yes. I'm sorry, I think last time we had minus IRD.
Okay, then is minus. Let's go with minus. Excellent. Thank you. Good. So if we look at the situation, what we have essentially, sorry. What essentially we do have is we need to find out what is the number of photons in mode C and mode D, and then I think the problem will be resolved. Okay, and of course what we get is just the probability. Good. So this is the let's say the state after the beam splitter. And if you do the expansion, this essentially is a Bernoulli expansion. And what we get summation of the choice of M out of N. Then we do have the T C dagger power of M. Then we do have minus IR D dagger power of N minus N divided by square root of n factorial acting on vacuum. Good. And M, of course, is changing from 0 to n. Good. So what I have done, I've just expanded, let's say, alpha plus beta power of n. And this is what happens. And I don't care that where C is located, where D is located, because they commute with each other. Okay, then the result will be summation of M equal to 0 to n. Let's simplify this. It will be n factorial divided by m factorial, n minus m factorial. Then the first one I have t power of m. The second one I have minus IR power of m minus, sorry, that should be n minus m. N minus m, that is n minus m. Then I have a creation operator for mode C, power of m, creation operator for mode D, power of n minus m, acting on 0, which is vacuum. Then the result will be divided by n factorial, of course. Divided by n factorial. Then the result will be summation of m from 0 to n, square root of n factorial, divided by n factorial, n minus m factorial, then t power of m minus IR, n minus m. The action of C dagger, power of m on vacuum, will create m number of photons, and the coefficient will be square root of m factorial. And the action of D dagger, power of n minus m on vacuum, will be square root of n minus m factorial. And each of them, they create m photon in mode C and n minus m photon in mode D. Okay, so it is not a surprise because the sum of the number of photons should be equal to n. And that's what we expect because it's a lossless beam splitter. So the energy should be conserved. Good. So now let's simplify a little bit more. What we get summation of m equal to 0 to n, square root of m factorial, square root of n minus m factorial. They will be simplified with the others. So what you will get essentially, you will get square root of n m as the coefficient. Then we do have t power of m minus I r n minus m. And then we do have m photons in C and n minus m photon in mode D. Good. That is after the beam splitter. Now the probability of detecting, look, probability of detecting m photons out of n photons, which this is sent to the detector, or let's call it inefficient detector, is given by this. So, which is, this is the state, then you will get the coefficient of this projecting on mode of m power of 2. So probability of m photons out of n for number of photons sent will be equal to n m, which is the square modulus, this is what I'm doing, t square modulus power of 2 minus ir square modulus power of 2. Good. Then that can be simplified as n divided by m eta square, because I assume that the transmittivity power of 2 is equal to eta, which is the efficiency of the detector, power of m. And the other one, minus I square modulus is 1, and r square is equal to 1 minus eta power of n minus m. Okay? So that's the probability that you will get m, let's say, m number of photons. If your detector is photon number resolving detectors, m clicks out of sending n photons. Good. All right. I think so far so good. Now the point is that how many photons am I sending? Am I sending really n photons, or I have a permission to look at the distribution of n photons? So can I send 1 photon? Can I send 2 photons? Can I send 4 photons? Can I send 10 photons? And out of them, looking only for the cases when 3 photons will arrive to the detector. Okay? If you do so, then the total probability of detecting m photon, summing over all n possibilities, will be given by summation of PMN multiplied by rho n, and then summing over n possibilities to infinity, when n must be greater than m, because I'm looking only for the cases in which I can detect m photons. Okay, so n should be greater than or equal to m in such a way that I can detect them. Then that is given by n equal to m power of infinity n m eta power of m 1 minus eta n minus m, and then what I will get rho n n. All right. Which distribution do you send? It's up to you. Are you looking for the action of these on a thermal light, or you are looking to find the action of these, which is the action of an inefficient detector on the coherent state, or photon number, is totally up to you. Okay? For the photon number that's equal to 1, because we assume that is for the Fock state, then the only things that you have to do is just n, then that will be simplified. However, if you want to look for the other actions, I mean the other statistic action, then you have to look at the rho and nn in one of those representations that we introduced them. So, for example, I mean those distribution, I mean quasi-distribution, probability distribution that we previously introduced. For example, for the case of rho and n, and we say that the Glauber distribution, Glauber Sudarshan representation, it is very realistic, but we know that in some cases they have a negative value or they don't exist. So that makes it more difficult to handle. But let's go with the Glauber representation. So in the case of the Glauber representation, do you remember what was the rho and n? So it was equal to d2 alpha. We are looking at the p representation, right? Then you have to look at the trace of rho essentially in the basis of coherent state, because if you remember, that was -1 and it was something like this. It was equal to d alpha w -1 of alpha, and then you had a t -1 alpha. T -1 alpha was alpha alpha, and then w minus alpha, the quasi-probability distribution was p alpha. Okay, so then if you look at this, then you will get that it should be equal to n alpha square modulus, which we can simplify this. It will be equal to d2 alpha p alpha n alpha, the projection of coherent state on the Fock states. Then it will give you, if I remember well, someone can correct me because it's a power of 2, then it will be alpha 2 power of n divided by n factorial. Then you do have e power of minus alpha power of 2. Okay, I think something like that. So remember, note that we had rho was equal to d2 alpha p alpha alpha alpha. And now what we are looking for, we are looking for the diagonal term of density matrix in the Fock basis. So essentially you have to multiply both sides by n. So it was rho, which is rho n n, and this is where I got this equation. Okay, all right. So then the probability of detecting m photons for any distribution, not necessary that you will get the result, but we know that for any distribution will be given by summation of n changing from m to infinity n m eta power of m 1 minus eta power of n minus m multiplied by the rho and n essentially, which rho and n is equal to d2 alpha p alpha alpha 2 power of n e power of minus alpha squared divided by n factorial. Consider that you can find P alpha. If you can find P alpha, that's excellent. If you don't find P alpha, then you have to look for other possibilities to find rho and n. Okay? Good. All right, so now let's simplify this. We get integral of d2 alpha, P alpha, summation of n changing from m to infinity, n over m, eta power of m, 1 minus eta n minus m. Okay, alpha squared power of n, e power of minus alpha squared divided by n factorial. Now we have to simplify this equation. Let's do that. Okay, integral of d2 alpha, P alpha. This term and this term, they are independent of the summation. So you can take them out. It will be eta power of m and e power of minus alpha squared. The rest, what we have, and also I can expand this. I can expand this, which essentially is n factorial divided by m factorial n minus m factorial. So m factorial from this also is independent of summation. So I can take it out, m factorial. Then the summation will be n changing from m to infinity. Then n factorial goes away. I have 1 divided by n minus m factorial. Then 1 minus eta n power n minus m. What else I do have is alpha power of 2 power of n. Good. Do you agree? Yeah. Okay. All right. So let's do, since the summation starts from m, let's do a change of variable, change of index. So I will, and of course I know that I have n minus m. So I will introduce n minus m as a k. Okay. So then the summation will be summation over k, changing from 0 to infinity. That will be 1 divided by k factorial. That will be 1 minus eta power of k. Now what I have here, I have alpha squared power of n. And n from here is equal to k plus m. So that will be alpha squared power of k. And also I have alpha squared power of m, which appears here. Good. This one is independent of the summation again, the new summation that we do have. Then the entire of this will be simplified to d2 alpha, p alpha, eta power of m, e power of minus alpha squared divided by m factorial. Then what else I have? I have alpha squared. So let's simplify this as well. So it will be eta alpha squared power of m, e power of minus alpha squared. And then I have the summation, which is summation k is from 0 to infinity. Okay, so 1 minus eta times alpha squared power of k divided by k factorial. What's that? Who knows what is the result of this summation?
It's an exponential.
Lovely.
Exponential.
Exactly. So this is nothing more than exponential of 1 minus eta alpha squared. Do you agree? Good. Excellent. So this is the result of this summation. Good. Then I have integral of d2 alpha p alpha eta alpha square power of m divided by m factorial e power of minus alpha square. Then I have e power of 1 minus eta alpha square. These two, they will be simplified, and then finally, what I get as an equation for p of m, remember, this is the probability. Let's write it as a, not get confused, probability of detecting m photons from any distribution, photonic distribution. Photonic distribution is given by this quantity, d2 alpha, p alpha, eta alpha square, power of m, divided by m factorial, e power of minus eta alpha square. Remember, what is eta? Is
The transmission
or what we started with,
efficiency.
efficiency of the detector. Okay. Now, who can tell me? Let's ask someone. So, Carol, can I ask you? Okay, we can do it together. Do you remember that we say why quasi-probability is important for us? We say that because we, first of all, if we know the distribution, we know the quasi-probability, okay? Then we can apply to that. And we say on the other side that we have to be careful with the operator and the quasi-probability distribution. So one of them is anti-order, the other one is order, right? If you remember that. So we say, for example, if you have an operator of O and you want to look at the expectation value of that, what you have to do, you have to do integral of d2 alpha. Then we have W of alpha with sigma, right? And then we have the operator of O should be minus sigma, right? Okay. And of course, we have to write it in the order of sigma, let's say minus sigma. Okay. For instance, if sigma is equal to -1, then that will be integral of d2 alpha and W of -1 of alpha and O of +1 of alpha. We drive all of those equations and we prove them essentially with the super operators. And that is identical to integral of d2 alpha of p alpha O of +1 of alpha. Can you tell me what is the meaning of this, if you remember?
Wasn't that just a way of, oh, what's the meaning of O?
Yeah.
That was the
-1 was anti-order and +1 was order.
that was the probability of detecting a coherent state. Or no, that's a, I guess that's not a state, is it? That was the coherent state traced with our operator, wasn't it?
Yeah, so somehow, I mean, that is true for the case of a coherent. So somehow we say that if we know the quasi-probability of P alpha, which is in this case is Glauber-Sudarshan probability, then the operator that you place it here should be ordered, right? If we have a dagger or whatever, you have to order them, and in such a way that all A dagger will be on the left side and all A should be on the right side. If we went with opposite one, if sigma was +1, then that was integral of, for sigma equal to +1. I just want to review, by the way, guys. It's not really related to our calculation now. Then we had to have the Q of alpha, and then we had to have operator in -1 alpha. So this means that the operator should be anti-ordered if you deal with the Husimi function, right? Here, what we know that since we are dealing with Glauber-Sudarshan probability, then we know that this is normal order or normally ordered operator, which means that all alpha and alpha dagger, A and A dagger should be set in such a way that A dagger will be on the left and A should be on the right. So can you tell me what is this operator now? This is an expectation value of an operator, right? Can you make a guess what is this operator? Don't get stressed, just
what would that be?
definitely should be normal order, right?
Mm-hmm.
Do you remember the definition of normal order? It was like that.
Yeah.
Then any alpha square should be replaced by A dagger A, right? So that is m factorial, nothing changed. What about the rest?
The rest would be an eta A dagger A to the m.
Exactly. And then?
And then you have e to the minus eta A dagger A.
Exactly.
Is
So
that some kind of thermal state, or?
No, it's not thermal state. This is the operator of inefficient detector, or a detector with an efficiency of eta. So this is the operator.
Just a question.
Yes.
This is why is this a normal order? How is this a normal order? Because there's an alpha. Sorry, an A before an A dagger.
So look, if we have we have A dagger A power of n, right?
Mm-hmm.
How do you write it as a normal order? You close your eyes. If this is normal order,
Oh,
you
okay,
close
okay.
your eyes and you write A dagger power of m, A power of m. That's all.
Okay, yes.
This is the definition that we had it for normal order and anti-normal order. If A dagger, we don't need that, but I'm just writing to review. M is anti-normal order, then you write it as A power of m, A dagger power of m, without doing any calculations. Just close your eyes. Okay? Clear?
Makes sense. Thank you.
Absolutely. So remember, the important point here is that this is an operator which, what it does, it's mimicking an inefficient detector. Okay. So if you see, let's say, who's working on quantum communication? Let's see who is working on quantum communication. Someone? Raise hand. Homodynamic detection? No one? No one is working on quantum communication or some sort of homodynamic detection, working with squeeze state and other stuff? No one? Okay. So, for example, if they give you a puzzle and they say that, look, go home and do the security proof that your detector is not working 100% of the time, but with efficiency of eta, and do the security proof and find out what it will be the action of inefficient detector in your setup, what you have to deal with, dealing with these operator that I have written here. You have to apply this to your state. Okay, good. All right, so this is the detector operator with efficiency of eta. It's eta get A power of n divided by n factorial e power of eta get A. Remember, of course, with efficiency of this, detecting m photon, m number of photon. Good. Let's look at the case when we have different distribution and we want to see what the detectors will show us. Okay. So, first case, coherent state. What I'm doing now, detecting m photons from a coherent state of alpha 0 with an inefficient detector of eta. Good? Clear? Is the question clear, guys? So I have a coherent state of alpha 0. It comes to a detector, which detector has efficiency of eta. And I want to understand how many m photons is detected. And later on, we will pose a condition on m, what it will be the m. M is equal to 2, m is equal to 3, or what? Okay? Good. What we have to do? Again, we know the action of the detector. We have to look at the probability. What we know about the probability? We know that the probability is a coherent state, and for the coherent state, it is easy to find Glauber-Sudarshan probability distribution. Then it's easy to find the action of the detector. What is the probability, quasi-probability distribution for a coherent state? Who remembers this from the previous lectures? Arman?
The delta function?
Exactly. Bravo. This is the quasi-probability distribution for a coherent state in Glauber-Sudarshan representation. Okay. Then we know that the action of the detectors, and we already did the calculation. So finding m photon, the probability of finding m photon, is given by integral of d to alpha, quasi-probability distribution of alpha, eta alpha square power of m divided by m factorial e power of minus eta alpha square. So now what we do, we just replace delta of alpha minus alpha 0. And remember, this delta always is a two-dimensional delta. So I think there's no need to discuss that. We know all of those details. Power of m divided by m factorial, then we get e power minus I alpha square, which consequently we get eta alpha 0 power of 2 power of m divided by m factorial. And then we do have e power of minus eta alpha 0 power of 2. Good? Again, let me ask you a question. Who wants to volunteer for a question which is not defined?
Go.
Okay, Eric, brave, brave heart. So, Eric, can you tell me what is the mean photon number for a coherent state? N average for photon, for coherent state.
It would be you take this.
No.
No,
We
okay.
have already calculated. We have already
Oh,
calculated.
yes, okay, yes, of course. Was it square modulus of alpha?
Exactly.
Hmm.
Square modulus of alpha. This is the average photon number in a it was a part of your exam, right? Midterm exam.
Yes.
And then if you substitute it here, what we will get, we get eta average photon number of n power of m divided by m factorial eta power of minus e power of minus eta average photon number of n. Let's look back to review what was the probability distribution of finding m photons in a coherent state, or in the coherent state of alpha 0. Who remembers this? What we had to do, just expand the coherent state in terms of photon number and look at the coefficient and do the square modulus, right? So let's ask someone else. Henry, can you tell me what is, do you remember this?
I think it's the same expression without the eta.
Exactly. Bravo. Well done. So it will be essentially alpha 0 power of 2, right? Divided by m factorial. And then we had e power of minus alpha square, which means that this is equal to, for us, it will be equal to n power of m divided by m factorial e power of minus n. True? Excellent. So the action of an inefficient detector, or with the efficiency of eta, on detecting n number of photon, is essentially reducing the photon number average from n to eta n. Nothing is changed. So if you replace this, if you replace the new n, the new photon number average with eta n, then you will get exactly the same probability. So in efficient detector, on the coherent state, what it does, just reduce the coherent state by square root of eta, the magnitude. That's all. Clear? Good. Another one. Now let's look at the thermal state. Let's see if, is it really the same story for the thermal state or is not? Who can make a guess?
I say no.
Manuel said no. Okay. Whom else?
I'll say yes.
I say yes as well.
Okay. Let's go yeses and versus no. Who? I think I hear 3 people saying yes. How many people they say no? Of course, Emmanuel said no. Whom else? Yeah, Kevin said no. Okay. Whom else?
I guess no as well. Just balance it out.
Eric wants to go with the with the democratic way. Good. Reza, what do you think?
I say yes.
Yes, okay.
We have all the theorists on the no side, so that looks pretty scary.
Okay, let's do the calculation. Of course, I can tell you what is happening. But I mean, intuitionally, you can find it out. But let's go with the case that you do the mathematics and just see what's happening. So let's do the calculation for a thermal light. So for thermal light, the first thing that we have to know is the probability distribution, right? The quasi-probability distribution, Glauber. And I remember, I think I tried this, or maybe it was a part of your homework, is 1 divided by pi square root, average photon number of n, and then is given by the, again, the Gaussian probability, which is minus alpha square divided by n. Okay, that's a quasi-probability distribution for the thermal state, or global Sudarshan representation for thermal state. Then the probability of detecting m photons by the efficiency of eta is given by integral of d to alpha, p alpha. Then what else do we have? The action of the detector, which was 1 divided by m factorial. Oh, let's go in this way. Same picture. It was eta alpha power of 2 power of m and e power of minus eta alpha square. All right? True? Okay. Now let's do this calculation for this specific probability distribution, which is integral of d to alpha 1 divided by pi n e power of minus alpha square divided by n eta alpha square power of m divided by m factorial e power of minus eta alpha square. Good. No mistakes, no mistakes. Okay. So the integration is on the complex plane of alpha. Remember, alpha is complex, which means that you do have alpha r plus I alpha imaginary. We already used that a couple of times. And then from this, also I remember that we say either you will go with the d2 alpha as d alpha I, d alpha r, d alpha I, or you can go to the complex plane, something like a polar coordinate. Then you can define alpha is given by absolute value of alpha e power of I theta. Then d2 alpha is look like absolute value of alpha, d absolute value of alpha, e power of, d theta. Okay, these are the two ways that you can look. I mean, depending really on the situation, you can go with either way. Good. So let's do that. Let's do the calculation. The probability of detecting m photons with an efficiency of eta then is given by 1 divided by pi average of photon number of n integral of d to alpha, which now is alpha absolute value d absolute value of alpha integral of d theta. This changed from 0 to 2 pi, and that is changing from 0 to infinity. Then what else do we have? What else do we have? We have e power of minus alpha square divided by n. And then we have eta alpha power of 2 power of m divided by m factorial e power of minus eta alpha square. Good. So integration on theta will give you 2 pi, because there is nothing really depending on theta there. So 2 goes away, right? Pi goes away with that one. So we have 2 divided by average photon number of n. Then also eta power of m and m factorial can be factored out. Then we do have integral of alpha d alpha e power of minus alpha squared divided by average photon number of n. And then we do have alpha squared power of m e power of minus eta alpha square. Good. Let's do the change of variable. Alpha squared selected to be u. Then 2 absolute value of alpha, the absolute value of alpha is equal to du. Then alpha d alpha is equal to du divided by 2. So essentially, let's do the change of variable. 2 goes away with the 2 that we have it as a coefficient. So we will get 1 divided by n eta power of m divided by m factorial integral of du e power of minus u divided by average photon number of n minus, sorry. Let's factor them together. Minus eta plus 1 divided by n u. And then I have u power of m. True? Yes, I think. Any mistakes?
Just to be clear, if our alphas weren't all square modulus, then we would have a real integral over the theta.
If we didn't have alpha square modulus, then at that stage I encourage you to do the integration with this.
Okay. Yeah.
Or you can do it with a d alpha star. Do you remember that I introduced all of them? So depending really on the situation.
Cool. Thank you.
Of course. Okay, so lovely. Now, who knows what is the result of this integral?
I feel like it's like a gamma function, but I can't tell what the argument is.
Who is person? Henry?
Yeah.
Exactly. It's a gamma function. But, I do always have mathematics open for these sort of problems. But honestly speaking, sometimes I believe that when I'm stuck in an island, I should be able to do the mathematics by myself, right? So let's go with, when you deal with these sort of integrals, is funny. I mean, they can teach you a trick that you can always get the result. So when you get 2 functions, which one of them, I mean, it hints you what you will get, okay? It gives you a hint what it will be the result. When you deal with 2 functions in the integrand, one of them is a polynomial, the other one is exponential. We know very well that the integral of the exponential always is exponential with a coefficient, and derivative of a polynomial will end one day, right? If you take the derivatives. So usually I use the trick. So you can take u power of m, take the derivative of these. So the first derivative will be m minus 1. The second one will be m times m minus 1 u power of m minus 2. And at the end, it will be m factorial, and just one step before being 0. And finally, after m plus 1 derivation, it will be 0. Okay? Then this is look like e power of minus gamma u. What is the integral of e power of minus gamma u? It is -1 divided by gamma. Let's do that. Let's do, oh, sorry. Integral of e power of minus gamma u du from 0 to infinity. That will be 1 minus gamma e power of minus gamma u from 0 to infinity. The infinity one will be 0. Then, assuming the gamma is a positive real, so this, which is it is, because eta and n, they are positive real. And then with n will be 0, so it will be 1 divided by minus gamma e power of minus gamma u. So that will be the first one. We do have e power of minus gamma u. Then the second one will be 1 divided by gamma e power of minus gamma u. The third one, again, will be 1 divided by minus gamma power of 2, e power of minus gamma u. And finally, that will be 1 divided by minus gamma power of m, e power of minus gamma u. Okay? Then you have to go with positive, negative, positive, negative, and finally that one will be positive 1. Then as a result, what you will get, if you product all of them together going from 0 to infinity, since you have u and u always will be 0 at 0, and you have e power of minus gamma u, which will be always 0 at infinity, all of those terms, they will cancel out each other. All of those terms will be 0. Just the last term won't be. Just this term won't be. And finally, what you will get 1 divided by n eta power of m divided by m factorial. Then you get m factorial divided by gamma power of m. Okay? All right. So then, what did we miss something? No, that's fine. M goes away, factorial. Then I do have eta power of m divided by n. And now I have to replace gamma, which gamma is eta plus 1 divided by n average power of m. The first integral, oh, that will be n plus 1, by the way. The last one will be n plus 1, and that will be n plus 1, n plus 1. The first one will be n. Yes, because it's 1 order more. Good. Okay. But you are right. Since we do have a m factorial Henry, m factorial is gamma of m plus 1, essentially. You're right. Good. So we got this probability distribution for the thermal light. Let's do a little bit of math. Okay. That will be eta power of m. That will be n divided by n power of m plus 1. Then I have n eta plus 1 power of m plus 1. Let's simplify this. That will be eta n power of m divided by 1 plus eta n power of m plus 1. Huh. Okay, now let's ask someone. That is the probability of detecting m photons with the efficiency of eta from a thermal light. What was the probability distribution of thermal light? Who remembers these? It was one of your homework question. So it was n power of m, or let's say go with the same notation that we had, 1 plus n power of n plus 1. that is the probability of finding n photon. Remember, n identical photon in a thermal source. Sorry, source. And here, what happened? The only thing that has changed is that the average photon number of n is changed to be eta n. Else is the same probability. Good? So how many people they say no? Yeah, I do see you guys. Yeah, it's identical for the case of thermal and coherent state. The last question before going to other cases, I mean, and other situation. Can someone tell me, is the probability distribution the same when you deal with Fock state? You should close your eyes and just tell me the result.
Is it going to be eta n again?
Really? Let me give you the question. I have n photons. I'm sending it to an efficient detector with efficiency of eta. I want to find out how many photons of m is detected. What is the probability of detecting m photons?
It'll be like binary, no? Like 0 or 1.
Can you tell me more? You can look at your notes if you have taken.
Wait, won't it be just the Bernoulli distribution we saw at the very start?
Exactly, this is what we start with. Okay, it is n over m, eta power of m, 1 minus eta power of n minus m. That's all. Then the probability, essentially, previously the probability was what? 1. And now the probability has been decreased to this. Okay? So what I want to tell you, it might not be a surprise for you if you don't see or you see or simplify the action of inefficient detector for the coherent state and thermal light. Just changing the mean photon average number to be changing from n to eta n. Okay, this is what you see. For coherent state, that will be the effect. For the thermal light, that will be the effect. But remember, for quantum light, no, it is not so simple. Okay, it changes a lot. Good? And that is the take-home message that you should know, that this is the operator that might just simply reducing the detection efficiency from, the photon average number of n to eta n for the case of thermal and coherent state. But when you deal with quantum light, which is the Fock state is one of them, then you may get problem. As a homework, try to do so for the squeeze source. You are sending a squeeze source and you want to see what is the probability of detecting them, n photons. Okay, might be a tough mathematics, but it tells you something. Okay, good. Now that we are in the probability distribution, I think I can do also a little bit of fun with the calculation. Yeah, we do have about 10-15 minutes, so let's do finishing this probability distribution, and then we can go with coherence optics. Okay, any questions so far? No, good. So the last thing that I want to touch today, I mean, just before going to the coherence or interferometer, is the concept of Poissonian and sub-Poissonian and super-Poissonian distribution, which is a little bit important. And we will see it when we introduce the G2 function in more detail. So remember that we had rho, and we just used them. For one of the case of quasi-probability distribution, it was d to alpha p alpha, and then we had alpha alpha. Okay, remember, this is nothing more than one of the representation, one of the quasi-probability representation that we had. We say that rho can be written as integral of d to alpha, w of sigma of alpha, and then we had t of sigma of alpha. For Wigner, sigma was 0. For Glauber, Sudarshan was minus 1. For Husimi was +1. Okay. So this is only for the case that sigma is equal to -1. Good. Now let us look at the photon statistic. What do I mean by photon statistic? I mean, we already talked about averaging and looking at operators and many other things. And even previously, when we deal with quadrature, this was part of your homework and many other questions that we deal with. It means that we have to look at the number of photons, average of number of photons, and we have to look at the variance of these, right? So what is going on with n minus the n average power of 2, averaging it. This is what we call it variance. How is the photon statistic, of course, power of 2, averaging it will change. By the way, this is the way that people in statistic, or some people in quantum optics, they will write it. It is, let's just simplify, because I know that maybe you get confused. Let's simplify this. So if you do the power expansion of these, it will be n minus n times n minus n. Then that will be n squared minus n minus n plus n squared. True? Averaging it. The first term will be n squared. Average of, let's say, sum of some, let's say, operators will be averaging of each individuals, right? So that will be n squared. The second term will be minus averaging of n. The second term will be n, and the final term will be averaging of n squared. True? So the first term will be n squared. N average is a constant. N average is a constant. This one is a constant. Then doing the average, it will be n average times n. That one again will be n times n. And finally, you will get n squared. Clear? And then that will be n squared minus 2n squared plus n squared, which is nothing more than average of n power of 2 minus n average power of 2. This is the variance that usually you are familiar with. So it's delta n square. Clear? So if I write it in this way, don't get surprised. Some people, they prefer to write it in this formalism. So essentially, the conclusion is that delta n square, which we define it as n square minus n square, is nothing more than this, which essentially what people they use is just simple variance. Good. Okay, now let's look at the variance of photon number. Let's look at the n square. N square means a dagger a power of 2. All right, true, which means that you do have a dagger a dagger a. Remember, I have not written normal order, anti-normal order, or symmetric way. I'm just writing in this formalism. Good? Good. So how do you calculate the average of n? Should I say that is given by the trace of rho n square? Agreed, guys? Okay. And let's do that. Let's do a little bit of mathematics. So it will be the trace of, or even before that doing so, let's do a little bit of expansions. So let's ask Felix. Felix, can you help me to make it normally order? I have to substitute these, right?
Yeah, we start with that one
So
and expand that as a dagger m plus 1. Yeah,
exactly. Okay, good. And then what I get here, it is a dagger a plus a dagger a. Do you agree? I have two terms.
Yep.
So the first term will be a dagger a. The second term will be a dagger a. So Felix, what is this?
This is n.
Exactly, this is n. And this is a normal order of n square. Do you agree?
Yep.
Guys, do you agree on this? How many people have problem with this derivation? I think it should be clear. We previously used that. Okay. All right. By the way, Manuel, your camera is off.
I know, but it's dark, so it doesn't matter.
Okay. Then now we can look at the n square as well. And what it will be the result of this? That will be, of course, it will be average of a dagger a power of 2. And this is again normal order of n power of 2. All right, so delta n squared essentially is given by n squared normal order plus n plus, oh, sorry, minus normal order of n power of 2. Okay, I have just written, someone may ask me why, Ibrahim, you didn't write the normal order for this one, because I don't care at the moment. I just say that this is the average photon number. Okay. Then let's do this. When I write normal order, I think it should be clear that which probability distribution should I use, right? I have written in this way that you will be helped to understand which probability distribution you should use for your calculation. So if it's normally ordered, what formalism should we go for?
The Glauber.
Glauber, exactly. So what I get from here, I will move this n at the beginning. Okay, so n is here, plus integral of d2 alpha p alpha. Good. Then n squared normal order minus integral of d2 alpha p alpha and normal order. There's no need really to write in normal order, but just to tell you the reason that I'm writing in this way is this. Okay. And finally, what we get n plus integral of d2 alpha p alpha. And do you remember when we had the normal order for n squared, which means that this is essentially a dagger, a, and that one is essentially a dagger, a. Do you remember that when we wrote it in this representation, the trace will be over them? So what we have to do, we have to just substitute a dagger with alpha star and a with alpha, right? So essentially, I have to really write that it's a trace over these. But anyway, I mean that will be alpha power of 4 because it's n squared. I get 2 alpha star and 2 alpha. And then when you multiply together, then you will get alpha absolute value power of 2. And then this term will be integral of d2 alpha p alpha alpha square power of 2. Clear? So essentially for classical probability, remember, because p alpha is look like classical probability. I think someone, when we discuss about the quasi-probability distribution, when I say that let's look at the calculation and find out what is the quasi-probability distribution for photon number, right, for the Fock state, I say, guys, in some cases doesn't exist. And that was a problem because n Fock states, they were not classical. That was the reason. Okay, so anyway, so what we will get for a quasi-probability distribution or classical representation of that, I get the variance in the photon number is given by average photon number of n plus integral of d2 alpha p alpha alpha squared minus integral of d2 alpha p alpha alpha squared all power of 2. And what is alpha squared in the classical version, guys? You can make a guess. Yes, go ahead, Henry.
Photons.
What?
Average number of photons?
average number of photons, which means,
It's positive?
yeah, of course, it's positive. In classical way means when you have a classical beam, what do you define for the property?
Intensity?
Exactly, is intensity. You are right, Henry. It's photon number average, but in the classical version, they call it intensity. So, by the way, this is power of 4, sorry. So, let's write it this way. Alpha 2 power of 2. Good, that is better even. Can someone tell me what is this? Felix, this is intensity, right? Intensity averaging over the probability. What does it mean?
So the total power?
Yeah, but it's a probability distribution, right?
Ah, so 1?
It is intensity average, right? You have a probability distribution and you provide the intensity, which is, remember, this is a function of alpha. You are doing the average of intensity or that probability distribution, power of 2, right? Because we have a 2 power here.
Yep.
What about this one? This is intensity, and that is intensity power of 2.
So just the, yeah.
Intensity power of 2, averaging it.
Yeah.
So in the quasi-probability distribution of P alpha, which is something like a classical way, what you will get n, the variance in photon number is given by n plus delta I power of 2, which is a variance in intensity. It is very interesting that the variance in photon number is the average of photon number plus variance in intensity. Okay? We will come back to this and we will have a little bit of discussion. So delta I power of 2 essentially is I power of 2, which is average of intensity power of 2 minus average of intensity power of 2. Okay. Clear? Good. Let's go with a few examples. As usual, what I love is coherent state. What we know about the coherent state, the quasi-probability distribution alpha is given by delta of alpha minus alpha 0 for a coherent state of alpha 0. All right? Can someone tell me what is delta I for coherent state? You have to replace it inside of the equations and you will get some results.
Is that just going to be 0?
Who said KM? Yes. It will be alpha 0 power of 4 minus alpha 0 power of 4. Exactly. That will be 0. Do you see it? Clear? I'm just looking at the videos to see if anyone having a question. So essentially that will be integral, and just let's do it, d to alpha p alpha alpha power of 4 minus integral of d to alpha p alpha alpha power of 2 power of 2. So if you replace p with the delta of alpha minus alpha 0 for both cases, then what you will get alpha 0 power of 4 minus alpha 0 power of 2 power of 2, which is essentially 0. That's all. Good. Haha. Now let's go for another one. What else? Nazanin. What is the next statistic that we have to look at?
Thermal state.
Thermal state. What is the probability distribution for the thermal state? Is P alpha. I think you were not here when I gave this example because we solved this for a detector. Is given by 1 divided by pi, average photon number of n, e power of minus alpha squared divided by n. I think it was something like that. So let's do that. We know the photon number, the probability distribution, the global one, and now replace it here. So we first of all we have to calculate d2 alpha, p alpha alpha square, alpha power of 4, which is essentially 1 divided by pi square root of n integral of d2 alpha, p power of minus alpha squared divided by n. Then I have alpha power of 4. Again, that is 1 divided by pi n. Using the same technique, I will do it in my mind. Guys, I may be doing mistake, but just correct me. So definitely I have a 2 pi. 2 goes away to the coefficient of 2. I have a pi integral of alpha, the absolute value of alpha, e power of minus alpha power of 2 divided by, oh, no. Okay, so let's do it directly because I have taken the 2 out. Okay, let's do that. And du, u power of 2, e power of minus u divided by square root of n. Okay, what I have done, I have done the same technique. So d2 alpha is equal to absolute value of alpha, d alpha, absolute value of alpha, d theta, and integration on d theta will give you 2 pi. And that is changing from 0 to infinity. Again, the same scenario, you do have u2, 2u2, and finally 0. Then you have e power of minus gamma u, that will be 1 divided by gamma, e power of minus gamma u, then 1 divided by gamma power of 2, e power of minus gamma u, 1 divided by gamma power of 3, e power of minus gamma u, and essentially at the end, I get 2 factorial. Okay, 2 factorial, which is 2 essentially, then 1 divided by n, 2 out of this, then I have 1 divided by gamma, which is gamma is n, so I get n power of 3, which is 2n power of 2. Good. All right, so I do have for alpha power of 4, let's do that calculation also for d2 alpha, p alpha, alpha power of 2. The same integral will happen. The only changes will be 1 divided by n integral of du u e power of minus u divided by n, which the result will be n power of 2, and there is no coefficient because it's 1 factorial, so it will be n, which is what we expect, of course. I mean, nothing surprising from here. So delta I square then is given by 2n squared minus n squared, which is n squared. It's not 0 anymore. Okay? Any questions? Okay. So let's review. We look at the delta n square. And what we found that is delta n square is given by n plus delta I square. For coherent state, delta I is equal to 0, which means that delta n square is equal to average photon number of n. Oh, let's write it in a better way because it's important. For coherent state, delta I square is equal to 0, then what we will get delta n square is equal to n. For the thermal light, what we will get? Delta I power of 2 is equal to n square. So means that delta n square is greater than n. Because it was n plus the delta I power of 2. Okay? Can you make a guess what's going on for photon number or Fock state? What will be delta I power of 2? Remember, delta I power of 2 is equal to d2 alpha p alpha, alpha power of 4 minus integral of d2 alpha p alpha, alpha power of 2 power of 2. Okay.
Would delta I squared be minus average of n because the delta n squared for the Fock state is 0?
From where you get there? Let me see you, Eric. Let me see. Oh, I do see you now. How did you get there?
Because the Fock state has a fixed number of photons. So delta n squared will be 0.
Yes, so you went from the other side. I want to go from this side.
Oh, but isn't the P not defined for?
P is not defined, or in some cases it will be negative. But I mean, you can calculate delta I, right? You can calculate delta I squared in any representation. It's up to you, right? So delta I squared can be calculated. And for those cases, delta I squared will be negative. Okay. Why? Because P is negative. This is the reason, if you remember, this was the reason that we call it quasi-probability. We didn't call it probability because we say that probability in classical mechanics will never be 0 or under 0. And in these cases, you do have a state which either P is not well defined or P is negative. Okay, so the probability is negative. So for quantum state, delta n square is below n. Okay. Now look at the situation, guys. What is the coherent state probability distribution, guys? The distribution that you have for photon number.
Poissonian.
Poissonian. So we call this Poissonian distribution. True? So if I have a distribution, which is that one is Poissonian, We will discuss about that in a proper language, by the way. I just want to get you familiar with the distribution. So this is the coherent state. And this axis is delta n squared. Poissonian is here, which the average is given by n. Sorry, the variance is given by average of n. Then we have two different regimes. One of them will tell you the variance is greater than what you have it by coherent state. Then we call this super Poissonian. Right? So it is this region. This is the super Poissonian region. And the other region is, by the way, this means here, okay? The other region is the place that your variance is below the coherent state, and we call that sub-Poissonian. And it goes here. One region is truly quantum mechanics or quantum mechanical, and you cannot have any classical probability describing this. Classical probability distribution is forbidden. Because P alpha is negative. While the other region, like what we have it here, is super Poissonian, which you do have the classical description for it. You have a classical probability for it. And the classical probability was, if you remember, we just draw that. So you do have a classical probability. Good. What about the coherent state? It's just at the border, right? So the border between quantum mechanics, so let's say quantum mechanical probability distribution, and classical one is defined by coherent state. This is one of the reasons that people, they call it coherent state the perfect classical quantum state. Good. All right, I think we will come back to these when we deal with the G2 function, but just I want to get you familiar with the description. Why, when we talk about classical and non-classical, we mean this, okay? And everything is defined by what? This, delta I square. Delta I square. I means intensity, right? And when you deal with intensity, we are dealing with second order of n, right? We are dealing with n square. Be careful. So then that's the reason that we have to go with the G2 function. This is purely quantum. It's not look like n, which is average, which we deal with a classical picture. N is something like a G1 function. Okay, we will let's have a stop of because I'm sorry, it's I speak too much. So in about, let's say, 10 minutes, we will come back and then we will find the argument, the basis, the foundation for the coherence theory, and then from these we will build up the G1 and G2 function. Okay, I will stop the video. Good. So now that we understand that there is something more that we have to explore about the quantumness nature of photon statistic, then we have to explore that. So we made a guess that it should be related to intensity, right? And now we will see this in maybe at the beginning of at the end of this lecture or beginning of next lecture, that is related to the G2 function. However, since not all of us we study optics in the past, so let's review a little bit about the coherence and understand what is the concept of coherency. So, do you remember that one device, quantum device that we built up together based on the operators was Mach-Zehnder interferometer, right? And I gave you an example. By the way, anyone solved that example? I say that you have a Mach-Zehnder interferometer. We built up what is the action of almost all of those elements that we used here. Let's say that we do, let's go with different color because I want to do some fun. Oh. Okay. Shoot. Okay. All right. So that is the beam splitter. That is the beam splitter that we had. And also we had two mirrors. And we built up all of the operators that are needed to do the action, to find out the action. And in addition, we had also a phase element here. We say that let's introduce a phase element that we had the action. Good. And our Hilbert space was up and down. At the end also, we had up and down. We solved the problem for many different cases. There's several different cases. And one of those problems was a coherent state. What's going on with the coherent state? If you feed a coherent state, at the end, we understood the action of the element. So I think I gave you a problem, right? And the problem was, what is happening when at the first beam splitter, I feed it with two photons? Anyone solve this problem? You had one photon up, one photon down. Anyone? No, no one? Okay. Try to do these sort of things. It's a little bit funny and interesting. I can give you even a little bit of, the action is simple, by the way. Action exactly what I gave it to you. You can go even with something more interesting. One photon from the up port has H polarization, and one photon from down has V polarization, minus inverted one. So it will be up one has V polarization, and down one has H polarization. This is another state. Look at that state as well. And remember that beam splitter, mirror, they will not act on the polarization. They will not affect anything there. So I'm asking you what's going on with entangled state if you feed it to a Mach-Zehnder interferometer. That's also an interesting problem. Good. Anyway, so now let's look at this case. And look at the case when we have a single photon entering to the interferometer. This is a Mach-Zehnder interferometer. And we want to understand what's going on if you send one photon on the up port. What was the result, guys? Anyone remember the calculation from the past?
A fake East-Angle state.
Not really. I say that don't
Ah,
call
no,
it
no, no, sorry.
It's like cos phi over 2 and over sine phi over 2 with maybe minus sign.
Both of them, right?
I think minus sign on the cos. Yeah.
And that was on the up port.
Yep.
Plus this one on the down port.
Yep.
Something like that, right? And then I say that in order to have a qubit, you have to introduce another phase element such a way that you can control the relative phase between these two elements. And that was, I think, was clear. So this is what we have, essentially. And if you remember, we did the calculation also for a coherent state, and at the end, correct me if I'm wrong, but I think we got something like that, cosine of phi divided by 2 with the negative sign of alpha going up, and then we had the sine of phi divided by 2 of alpha going to down part. This was for coherent state. So the result is not surprising if you do it with a coherent state or if you do it with a single photon state. At the end, what you will get, let's say I'm looking at the port of D here, the exit port of D. Then I want to understand what as a field do I get there, right? Clear? I'm looking to get the information about the field that is coming to the port D. So one of the arm that electric field is propagating is the black one, which is coming here with the mirror. The other one goes down and comes back to the beam splitter. And at the beam splitter, they will be interfering together. True? So I will call it the upper arm and lower arm. And upper arm. And those two are the beam splitter. And I'm looking at here. Good. So electric field essentially at this part will be given by electric field that is coming from the upper part with the coefficient, of course, which is propagated through the black, let's say, region, the black path. So you have exponential of I, K. I call this length LU plus the photons that is coming from the, or let's say the port of the electric field, part of the electric field, which is coming from the lower part, which is given by E of down, E power of I, K, L down. Remember here, I'm using the complex notation. Now, let's say in about 5 to 10 minutes, we will go to the second quantization formalism, and we will see in a proper way. But for the time being, remember that I'm dealing with a complex formalism. Okay. So what is this detector? It is what is this electric field? Is electric field at the detector D, which is located here. This is the electric field here. Remember, I don't care about R, I don't care about T. because I know that from the black curve or pass, the first beam splitter, it will be reflected. On the second beam splitter, the black will be transmitted. If you go with the red will be transmitted first, and then the other side will be reflected. So it is almost symmetric, okay? That's the reason that I write E, U, and ED. Do you agree with me that EU and ED, they are identical? I will call them E0. But the electric field will oscillate with e power of I omega t with a negative sign. We have the oscillation also in time. Good? Excellent. So then the electric field at detector is given by E0 power of 2. E0, e power of I omega t, which will be factored out for both paths of black and red. And then what I have e power of I k L u plus e power of I k L d. I have already neglected the polarization degrees of freedom. I assume that the field has the same polarization because it starts from here. It's H polarization, and I assume that the mirror, or V polarization, I assume that mirror beam splitter, they will not change anything there. Good. Does detector see electric field? Is there any detector that, our detector does not see the electric field. What it sees is intensity, right? Or irradiance, if I want to be very careful with the definition. So essentially what we are seeing is E times E star, irradiance or intensity. The definitions are very different, but people, they use it. So if you look at the E star, then you will get E0 power of 2. Exponential term goes away. And then what I get, e power of I k L u plus e power of I k L d times e power of I k L u with a negative sign plus e power of minus I k L d. Good. Right, excellent. So intensity essentially is given by E0 power of 2. Then what I have 1 plus 1 plus e power of I k L u, or let's write it in this formalism, k L u minus L d plus e power of minus I k L u minus L d. I'm sure that many of you have seen this equation previously, but its review is okay. So this expression can be simplified further. What you will get E0 power of 2, and that will be 2 plus 2 cosine of k Lu minus Ld. All right. So you can even simplify further. You can take away the 2, and then you will get 2 E0 power of 2, 1 plus cosine of k Lu plus, minus LD. We can simplify this further as well. 1 plus cosine of, I have never remembered these equations. It is 2 cosine square of theta divided by 2, right? It will be E0 power of 2 cosine square of KLU plus, sorry, minus LD divided by 2. Okay. This is totally classical. So we inserted, let's say, a continuous wave coherent into the Mach-Zehnder interferometer, and we are looking at the other side, and we see what we get there. Okay. And essentially, what we get there is we get 4 E0 power of 2 cosine square of phi divided by 2. This is the difference. This is the relative phase difference between the two. Essentially, we had, from the last calculation, we had this probability. It was just cosine phi divided by 2 power of 2. That's the probability. Good. What does it mean? It means that if I have the detector here, which it records the intensity, then if I change the phase, which means I'm changing KLU minus LD divided by 2, which is pi pi LU minus LD divided by lambda. So essentially, I'm changing this. Then, as a result, what I get, I will get fringes. Okay. Symmetric fringes with the same frequency, which is dictated by this in a linear way, I mean, in terms of the value of phi. And at the 0, it should be maximum, by the way. I draw it in a bad way. So by changing phi, or changing the difference between the LU and LD, then you can control what is happening with intensity at the detector. Good. This is what we call it interference, essentially. Let's look at the visibility of these fringes. They have a maximum intensity, and we have a minimum intensity. Define visibility as intensity at max minus intensity at minimum divided by intensity at max plus intensity in minimum. Intensity at minimum happens when phi is equal to pi, okay? Which means that LU minus LD is equal to 1 wavelength. Is that true? 2 pi divided by lambda. Wait for me, because that should be phi equal to this one. So L pi divided by L, lambda is equal to pi. Yes, that's true. So LU minus LD is equal to lambda. And if you do a little bit of math, you will see that the maximum happens, it is 4e0 power of 2. That is simply is given by cosine of k LU minus LD. Okay. Which in this case is 100% the visibility. So in this, for this specific case, you don't see too much difference because it's a monochromatic light, is coherent light. But happens, there are cases when LU minus LD, when you change them, the fringes disappear. So what you will get as fringes, you will get something like this. So let me show you as an example. You will get fringes like that, but then the fringes, they will disappear. Okay. There are cases in which the fringes visibility depends on LU minus LD and vanishes when it is large value. Okay. All right. So that is, I mean, you are all familiar with this situation, with the case that when you deal with the classical interferometer situation. So you get a coherent light, an electromagnetic field, you send it to any sort of interferometer, and then you will do interference. And the result of interference depends on how the two beams, they arrive at the same time, okay? Or spatially, they are overlapping together. And that is what we call it, interferometer. And there are different types of interferometers. One of them is look like a Mach-Zehnder interferometer. There are other ways which we call them like a Young double slit, or Michelson interferometer, or Fresnel prism, and etc. So they can be divided in two different categories. Either the wavefront of the beam will be splitted, or the amplitude of the beam will be splitted. Okay. So this was one of the cases that amplitude has been splitted. So the photon, or let's say the coherent state or electric field, will be in superposition of two different cases. Okay, all right. So now let's look at that calculation, but now with a different view. So again, electric field is given by EU plus E down, right? This is what we discussed. But now we are not using the complex formalism. What we do, we remember that electric field from the quantization is given by the positive frequency and negative frequency. True? But still, I don't want to put the annihilation operator and creation operator. I just want to tell you that it has two parts, positive and negative, because that will be used also later on. So one is on the positive frequencies, and the other one is on the negative frequency. Okay, if you remember, one was given by, if I remember the expression, e power of I k dot r minus omega t, and the other one was e power of minus I k dot r minus omega t. Good. So then the EU essentially is given by EU, the positive part of frequency and negative part of frequency. Remember, both of them, they have the same amplitude. Okay, the only thing is that we want to deal with the negative and positive part of the frequency. Everything is identical. It looks like having the form of complex conjugate that we do have. We want to make it real, so we are adding the other part of the complex Hermitian conjugate of the electric field to it. The same story happens for ED. So we do ED plus ED minus. Okay. Note, E plus is going with e power of minus I omega t. E minus, it goes with e power of I omega t. Okay, good. What's going on with irradiance or intensity? Simply, we look at, since each of those, they are real quantity, now we are going with the product of them. We don't go with the complex conjugate. So let's go with the product of them. So we have E plus E minus plus E plus E minus D. Multiply that by itself. EU plus EU minus. Okay. How many terms do we get? 16 terms, because it's 4 terms multiplied by 4 terms. So let's write them down. E plus U, E plus U. E plus U, E minus U, E plus U, E plus D, plus E plus U, E minus D. I do it for G1, but I will not do it for the G2. I'm just doing it because I want to give you the feeling. That's what's going on here. Then the second term will be plus E negative U, E positive U, E negative U, E negative U, plus E negative U, positive D, plus E negative U, E negative D, plus E positive D, positive U, D, A positive U.
Does it need to be the conjugate of the second terms or no?
No, because they are real now.
Yes. Okay. Cool.
They are real,
Thank you.
of course. When I write it down, then we can discuss about the physics of that. Plus U minus D E minus U. Sorry, guys, it's a little bit long, but they are important things which we will be using them in the future. D plus E negative D E negative D. Good. So we have 16 terms. Positive is positive superscript is going with e power of minus I omega t, and negative superscript goes with e power of I omega t. Agreed? All right. What is the result of this? Is a function of time? Yes. Is it a function of position? Yes, also is a function of position. Remember these expressions. And that will be different for U, and that will be different also for D, because they are coming from different paths. All right? So intensity that we do have is a function of R1 or RU and time, and also R up, down, and time down. Okay? Do you agree? So essentially, this is what we get. The two fields are coming together, they will interfere together, and then this is what we will get it as an intensity. True? Lovely. And I want to understand, are our detectors so fast to see these changes? Because look, we are talking about frequency of that we deal with. Usually the frequency that we deal with is 10 power of how many hertz? 15 hertz. This is the frequency of visible light that usually we use them. 10 power of 16 to 10 power of 15 is that between that range. What is the fastest detector that we can get?
Picosecond.
Reza say picosecond. Okay. Many of you worked in the laboratory, physics, manual, flow, right? Let me see. Kate, Henry, I'm sure that you also worked in the lab. Eric, no, he's purely theoretician. Arman, yes, you worked in the lab. What is the response time of a detector? Arman? Sorry.
I'm not sure off the top of my head.
So any of those detectors will work based on interaction of light and matter, right? What is the interaction scale that you expect that the light will be emitted? Sorry, light will be absorbed by material. Order of nanosecond picosecond, not more than that. So it's 10 power of, the fastest one that we can get is 10 power of, let's say 10 hertz, which is, this is what I'm telling about the time. resolution, then you will get the frequency of 10 power of 10, not more than that. So these frequencies already 5 order of magnitudes higher than these. True? So if that is the place that your detector is able to see from the time of 0 to here, let's say 0 to 1 picosecond, or let's say 10 picoseconds, should say 10 picoseconds. I think if you want, I want to be careful with the plot that I had it here. It's 100 picoseconds. Yes, it's 100 picoseconds. Then in this interval, I have 10 power of 5 oscillations. Until here. Okay. So my detector is not able to resolve that oscillation of intensity. Okay. So it sees the average of the fluctuation or average in time. So due to detector property, what you will see the average of this intensity. This is the job of your detector. Okay, when you do see the average of this, now you see the slow oscillation of the electric field. Okay, sorry, the slow oscillation of intensity, because you may have different oscillations. For example, let's pick up this term. Let's pick up this term. Let's pick up this term and that term. 4 terms. Let's call them term number 1, term number 2, term number 3, term number 4. And we will see what's going on with the oscillations of those terms. The first term, what is the oscillation of it? So, Arash?
Yes.
Yeah, what is the oscillation term? The time dependency.
Omega.
Assuming that both of them they are oscillating with the same frequency.
2 omega.
E power of I minus 2 omega.
Minus 2 omega.
Lovely. So it goes with 2 omega. That's important. So someone else, Flo, can you tell me what's going on with the second term? Second term here is U minus E D plus.
Yeah, it cancels?
Exactly. It's a DC term. Has no oscillation. Is a DC term. No oscillation. What about the term 3? Let's go Tenglu. The third term. You are muted, Tenglu.
Yeah, I was thinking it should be plus, if I'm not mistaken. E power.
It is E plus, E minus.
Sorry.
Both of them, they have E power of, one of them has E power of minus I omega t. The other one has E power of positive I omega t.
Then it should be 0.
Okay, it's a DC term again. So let's ask someone else. Chandler, can you tell me about the fourth term?
E to the I to omega t.
Lovely, exactly. So now you do see that if there is a, I mean, you find a pattern here. So if there is plus plus, the frequency will be double. When it's negative negative, the frequency will be minus double, right? When it's negative plus, negative plus, negative plus, negative plus, negative plus, all of those terms, you do have a DC term. Okay? And for the rest, you, as we discussed, that will be different. So looking at the DC term, so since we are looking at the intensity averaging in time, all of those that they are highly oscillating, they will cancel out each other because averaging of any periodical function will be zero. So assuming that you have a periodic function of these, which is oscillating between 1 and -1, what is the average of these? Definitely zero. True? Okay. So the same scenario happens here. So what we will get at the end, we will get those terms that they have plus minus sign, which should be 1, 2 term, 3, 4 term, 5, 6 term, 7, 8 term. Okay. Okay. Good. So it will be the average of E plus U, E minus U is U, yes, okay, plus E plus U, E minus D. That's the first term, plus, I can write them right just like what it should be look like. So let's write it in this way. Okay. The second one is EU minus EU plus EU minus E plus D. Then I have ED plus EU minus plus ED plus ED negative. And finally, I do have ED negative E plus U plus ED negative ED plus. Okay. So I have 8 terms. What about this term and that term? ED, we say that E plus and E minus, they have the same amplitude if they are coming from the same field. So essentially that will be the first and the last term will be intensity of U and intensity of D. Okay. Which we do have also here. And we do have it also here. So it will be 2 of those. So yeah, fine. Good. Now what else do we have? We have E plus U. E plus U, E plus U, E plus U. We should have that one as well, which is here. So I do have plus E D plus U, E D negative. plus the last one, E negative, E positive D, E negative, oh, let's write it the other way because I want to go with the conjugate. E negative U, E positive D. Okay, do you agree? Do you agree that this is the complex conjugate of that one? Do you agree? Okay, let's write that down. So we do have 2I of U plus I of D plus 2 real parts of E U E D. Okay, let's look at the notation that I have just to be clear. That will be negative. I will go with the negative positive. Okay. So essentially, people, they call this term G1 function. Okay, and I will elaborate it a little bit more on this, and you will get further feeling about the situation. So let's take away 2, and sorry, 2I, that will be 1 plus 2 divided by I U plus ID. And then I will take away I U average and I D. And I will write that real part of E U negative positive D divided by square root of IU square root of ID. And then finally, I will get that coefficient out because I don't want to have it with myself. So I will go with IU plus ID. Okay, what I have done, I divided this by square root of IU square root of ID, and I multiply this side with that quantity. And also I factor out the intensities, the sum of the two intensities. People, they call this term entirely G1. Simply, you can call it U and D, but now we will define them. And this is first order correlation function, or G1. Note that one of them should be negative, the other one should be positive frequency. Okay? Is a DC term, is not an AC term. Clear? Good. Okay. And no need to go with the discussion. I mean, you can look at the first scenario, which was totally classical, and from the classical picture, I derive what is the visibility. Also, visibility here will be dictated. I don't want to go with the identity relation. Visibility is proportional to G1 function, which G1 function is given by EU minus E plus D divided by square root of EU minus EU plus ED minus ED plus. Okay? That's the relation. I want to understand who is walking. Flo, your mic is not off, sorry. Oh, you, okay, thank you. Good. So that is essentially what happens when you deal with two fields of that going down, and one is coming from the upper, let's say, port, the other one is coming from the down port, and they will do the interference, and that will be the expression that dictates what's going on with the visibility, okay, and the interference then. And we derive these based on the entirely classical picture, only assuming that your detector has a certain response time. And remember that this bracket means that time average. So you can say essentially that is given by 1 divided by time, 0 to t of your function, dt, and that's function. T is changing to going to be infinity. That's essentially what we do with the time average. All right. So remember this. Now, let's apply this to the previous problem that we had. So one of the photon is coming from the upper port, which is e power of I k dot r. And one is coming from the upper port, so the upper port will be, let's call it RU, and may have a phase due to the phase element that we introduced there. So it should have up, okay? And this phase can be even random, is up to you. It can be depending on the, maybe it's scattered from some material there. So maybe you have an atom, or let's say sequence of atoms or cloud of atoms, which they randomly interact with the photon, and maybe it gives a random phase, which depends on the position as well. So it maybe depends on the RU and the time that arrives there, okay? And for the photon that is coming from the down port, the same scenario. It can be e power of I, k dot r, down plus I, phi down of r, u, d, and t. Okay. Remember, what I have written here is related to the positive part of the frequency, right? And if you go with the negative one, you have to go with the conjugate of this, because it's minus I k dot r and minus the phase, because the total of the two should be equal to a real quantity, okay? So then if you substitute it here, G1 term will be proportional. I don't consider the denominator, because the denominator will be equal to 1, and the average of 1 will be equal to 1 again. So it will be proportional to what we have it on the denominator. It will be e power of I K dot R D minus RU plus I phi D minus phi U. Okay. This is what happens. Remember, this average is over the time. Okay. So if phi is time dependent, then you are in trouble. You cannot simplify this. That will give you a constant term. You can take it out from the integral, but that term of the phase will play an important role in your calculation. Next lecture, I will drive what's going on with the G1 when you have, let's say, a stochastic interaction with atoms, when you get a random phases there in two different scenarios, when you have a collisions with atoms and when you have a broadening as a Doppler shift. And we drive what is going on with the G1. And then we are prepared to go and move to the G2 because the same mathematics will be used for the G2 function as well. And then, of course, we write the quantum mechanical picture of that, and we will discuss the Humphrey-Brown entries. So I think I don't want to hold you too much here. We are done with today's lecture. I will encourage you kindly, please go and read this part carefully. It is important. If you don't understand it, then next lecture we will be in trouble. Okay, I will stop the video and then I wish you a great week.